Most mistakes in vibrational analysis do not come from solving the equation. They come from setting it up wrong. In this video, we derived the equation of motion of the damped single degree of freedom oscillator step by step, then show where the eigenvalue actually comes from. Here we see a mass that can move vertically in the z direction, and the positive z direction is defined downwards. We have a spring with stiffness K, a damper with damping coefficient D, and an external force acting downwards. In addition, the gravitational force is acting as well. To derive the equation of motion, the very first step is to draw a free body diagram. In this diagram, we include the body with a mass m, and we draw all forces acting on it in the positive direction. Since z points downward, all force arrows are drawn downward. Let's start with the spring force. The spring force is given as Fk is equal to minus k times z. The minus sign appears because we draw the force arrow in the positive direction, but when the mass moves downwards, then the spring is stretched. The restoring spring force acts upwards. Therefore, we obtain minus k times z. We do the same for the damper. The damping force is also drawn in the positive direction, and we consider that if the mass moves downwards with a certain velocity, the damper generates a force proportional to the damping constant d acting upwards. Therefore, this force is also negative. Next, we include the external force. In most cases, that's a harmonic force. So the external force is given by F external is equal to F hat times the sine of omega capital T. Here, F hat represents the amplitude of the force, and omega capital is the angular excitation frequency. In addition, there is another external force, namely the gravitational force. This force acts constantly downwards and has the value m times g. Now, one force component is still missing, which is the inertial force according to Newton's law. Fm is equal to minus m times z double dot. The faster a body is accelerated, the larger the opposing inertial force proportional to its mass. Since this force always acts opposite to the direction of motion, and since we define positive z downwards, the inertial force acts upwards and therefore also appears with a minus sign. At this point, all forces have been drawn systematically, with the arrows pointing in the positive direction. We can now move on to the next step and write the dynamic equilibrium in the z direction. All forces in the z direction are summed and set equal to 0. This describes a dynamic equilibrium, meaning all forces balance each other and their sum is 0. So we insert the mass force, the damping force, the spring force, the external force, and the gravitational force, sum them up, and set the results equal to 0. Because all forces were drawn in the positive direction, we now simply add them up without worrying about the signs. This is exactly where the biggest modeling errors usually occur. If we insert all terms and rearrange the equation such that it starts with a positive term, we obtain mz double dot plus dz dot plus kz is equal to f hat times sine of omega capital times t plus mg. This is the differential equation of motion of the system. It depends on the degree of freedom z and its time derivatives, while all remaining quantities are constants. From the stiffness and mass term, we can now derive the natural angular frequency of the system. Omega 0 is equal to square root k to m, denotes the undamped angular frequency. This means that if the excitation frequency, omega capital, is equal to this natural angular frequency, resonance will occur in this region for low damping values. If you want to learn more about the step-by-step modeling of dynamic systems, check the link in the description.